Let me thank you for the invitation from me and my colleagues to such interesting conference. First, I want to introduce myself. My name is Georgi. I'm the head of laboratory of intelligent monitoring of the Institute of Continuous Medium Mechanics of Federal Example. And some words about laboratory. Certainly, our laboratory solving problems of predicting stress strain statement of constructions or buildings in the zone of technogenic impact caused by mining operation or aggressive environment. Last 15 years, we made more than 60 variations of monitoring systems of structural health problems, which includes more than 2,000 sensors, different sensors. But now, in this year, we have investigated some new tasks, new problems that exist some tasks in new region, Arctic region, with permafrost, where some problems indicate with changing of climate. And permafrost is defrosting. And structures or buildings in that region taking large displacement, the changing stress strain state of such object. And we need to produce or to create new versions of our systems that includes new sensors. And this report is about new methods. I think this is very simple and elegant method to predict the rating of elastic characteristics of permafrost. Let me show you. Here you can see Acheson relevance about our work and outline of the report. How to talk about conducting experiments of pile-zoned Boreton's frozen soil continuous monitoring of vibration of ground of system pile soil law, conducting experiments of pile Boreton summer soil, determining dynamic parameters, natural frequencies, about continuous monitoring of background and impulse impact in the soil pile system with actuator, and finally climate modeling. In this slide, you can see pile zone. Here it is. In winter conditions, the pile was installed in frozen soil. That's about 1 meter. The ground in the area of the location was cleared by the snow. You can see pile parameters. This is steel pile, diameter 57 millimeter, length 1.2 meter, mass 6.5 kilogram, and depth on the ground is about meter. Load parameters is steel metal cylinder, and height of the pile, diameter 1.255 millimeters, height 150 millimeters, mass 42 kilograms. Sorry. Experimental equipment shown in this slide. We have 3-component accelerometer, ADXL 355, recorded on microcomputer, Raspberry Pi, and computer for data processing. Here you can see characteristic of 3-axis digital accelerometer. Here it is, and here it is on the load of the pile. In summer conditions, and after installation of the pile in the cold period, winter or early spring, an experiment was conducted to detect natural frequencies of the system using external influence on the pile with the load or the ground. There, the ground temperature was about -2 Celsius degrees, and full section is understood to be blown to a massive cylinder in different directions. Here you can see sensor position on the cylinder mass. And next. This is response to impact by the directions. And here you can see Fourier spectrum. Then we measured the background vibration caused by natural reasons with wind or vibration from mechanism in the territory of experiment. Measurements were made during the time period corresponding to the seasonal flowing or defrosting of the ground, March, April, in spring. And here you can see signal in its vibration components, spectrum, and tone sweep of the spectrum in time. Tone emission Fourier spectra were previous slide, were constructed to analyze changes in frequency. Each vertical bar corresponds to Fourier spectrum for a certain time and date, where the darkest colors show the signal intensity for frequency. For clarity, normalizing is performed by a maximum value of each Fourier spectrum. Here you can see components X, Y, and Z. The difference between the change of the frequency spectrum with the time is observed. And here is frozen soil, then sowing or defrosting, and summer period. We can see changing of the frequencies. Here you can see dynamic frequencies in the direction of X. Black circles evaluation of natural frequencies. Green line temperature of the cylinder mass or area. The red temperature in the pile at the depth of 30 centimeters. You can see different frequencies in earlier period of experiment and in summertime. Dominant frequencies in the direction of here, the same. And verification of natural frequencies after or defrosting. Upon completion of the continuous observation, the natural frequencies were again estimated using external influence, where temperature was plus 15 degrees Celsius and ground temperature was about 5 degrees Celsius. And we can see the frequencies during the water period for X, Y, and Z direction, and frequencies during the winter period. And it's changing. Conclusion: after thawing on the ground and with increasing air and ground temperature, there is no further decrease in the frequencies of the ground by alert system. Second experiment, measurements of impulse vibration. You can see in this slide another pile with actuator, with solenoid, and another experiment. In this slide, you can see change in frequencies. On time and temperature were plotted. Dependence of value function temperature and dates.
1 week?
Yes, 1 week.
Great.
Tone images of Fourier spectra were constructed to analyze changes of frequencies. Each vertical bar corresponds to the Fourier spectrum for a certain time and date, where the darkest colors show the signal intensity or the frequencies. For clarity, normalization is performed by the maximum value of each Fourier spectrum. And you can see how changing frequency by background measurements or by impulse vibration by the actuator. Then we modeling such system, numerical and analytical method to determine the modulus velocity of coil is presented. Experimental results on the dynamic behavior of pile embedded in soil mass and numerical results based on the finite element method are given, providing the construction of the depends of natural frequency of vibration of the pile and the modulus of velocity. Here you can see here frequencies and velocity modulus on the ground. First four natural frequencies. First two is bending, third is rotating, and four is vertical form of frequency. And here some conclusion. Thank you.